Hello and welcome to this video on the R method, the R transformation, or simplifying A sine x plus B cos x, whatever you want to call this topic. This is just a revision of this topic, so if you're looking for a more in-depth video that explains the concepts underlying everything, then you can have a look at one of my other videos in the channel. So we're quite often asked to work with functions where we have a mixture of sine and cosine, and we have techniques that we can use to solve equations with a mixture of sine and cosine, nominally dividing through by cos and getting tan. But we can also think of the A sine x plus B cos x problem as a transformation of a graph. And this is what this does. Okay, we're turning this expression here, 3 sine x plus 4 cos x, into this form, r sine x plus alpha. Now, I want you to really make the link, if you haven't already, that r sine x plus alpha is a transformation of the graph sine x. So, that's not right. You can tell it's early in the morning. Here we go. Right, so if I think about the graph y equals sine x, I can quickly sketch that, and I know that it's like that, beautifully drawn as ever. I know that it exists between 1 and minus 1, so its amplitude is 1. I know that it has a period of 360 degrees, or obviously 2 pi radians if we're working in radians. So, you know, that's the basics of the sine curve. If I plot the curve y equals r sine x, where r is just any value, then what happens is it affects the amplitude, so that the sine curve no longer goes through 1 and minus 1, it goes through r and minus r, because this is a transformation in the y direction and it's a stretch. So we're taking all of the y coordinates and we're multiplying them by r. So instead of going up to 1, it goes up to r. Say, for example, r was 5, then this would be 5, and this would be minus 5. It would be stretching that graph. Now, say, for example, I want to shift the graph and I want to say r sine x plus, let's say, for example, x plus 30. Then I would adjust my sketch, and I would have, instead of going through at 0, 0, it would now go through at minus 30. So we kind of have this thing going on. Okay, so instead of crossing here at 360, it would now cross at 330. Instead of crossing here at 180, it would now cross at 150. And instead of crossing here at 0, it would now cross at minus 30. And instead of going up to 1, we've got our r, and below we've got minus r. So this is the graph of, for example, y equals r sine x plus 30. So what we're doing when we apply this transformation method is we're turning 3 sine x plus 4 cos x into a form where we know what the graph looks like. It's very difficult to picture the graph of y equals 3 sine x plus 4 cos x, but it's a lot easier to picture the graph of something multiplied by sine x plus an angle, because it is just a transformation of the graph. And you really need to understand that connection. Otherwise, the problem-solving questions, the real-life modeling questions, are going to prove very difficult. So let's get to how we actually turn this into this. So I'm looking at 3 sine x plus 4 cos x. And I'm turning it into this r sine x plus alpha. Okay, that's the point of this. Now, there's one simple process, and it's the same process every single time. Okay, the first step is to evaluate r. Now, we used Pythagoras' theorem for this. We take the numbers here, the coefficients of sine x and cos x are a and b, if you like, 3 and 4, and we square them, we add them, and we square root the answer. And that's always the way, okay? It's always the case. This number squared plus this number squared, square root the answer, that is your r value. The easiest thing in the world to find. To find the alpha, we have to do a little bit more work. So I'm going to go back to this, 3 sine x plus 4 cos x, and I'm going to expand this sine x plus alpha. Now I'm using the expansion of sine a plus b, which again will be covered in another one of my videos that you can go back and have a look at. So we've got sine of a plus b, sine x cos alpha plus cos x sine alpha. And we've multiplied everything by r. Okay, so I'm writing way too much work in for this, but it's just important that you see every single step. So we've got r sine x cos alpha plus r cos x sine alpha. Okay, that's how this works. Now we're going to have a look at comparing coefficients. So over on the left here, we have sine x being multiplied by 3. On the right, we've got sine x being multiplied by r cos alpha. Okay, just comparing those two things, coefficient of 3, coefficient of r cos alpha. That means that r cos alpha is equal to that 3. It has to be. Okay, the number of sine x's on the left has to be the number of sine x's on the right. Next, I'm going to do exactly the same thing for cos x. I'm going to look at the coefficient. I've got 4 cos x's over here on the left. How many cos x's do I have on the right? I've got r sine alpha. So r sine alpha is equal to 4. Has to be. These two sides are identical. Now, how do we use that information? Well, quite straightforward. We can say that tan alpha is given to us by r sine alpha divided by r cos alpha. Why does that work? Well, r divided by r gives us 1, effectively cancels out, and sine alpha over cos alpha we know is tan alpha. So r sine alpha was 4, r cos alpha was 3, so tan alpha is 4 over 3. So we just can take arc tan of 4 over 3, and then we get our answer. So this is where we have to be mindful of, are we working in degrees or are we working in radians? I can see from this question, we're working in degrees. You look for the clues within the question, so make sure your calculator is in degrees. That's what I'm doing right now. And we'll do arc tan of 4 over 3, which comes out as 53.1 to 3 sig figs, or 1 decimal place as required in the question. So that tells us, we can now write 3 sine x plus 4 cos x is absolutely identical to 5 sine x plus 53.1. So all of a sudden we've gone from a function where I wouldn't have a clue what this looks like if I was to try and sketch the graph, 3 sine x plus 4 cos x, don't know. But 5 sine x plus 53.1, well, that's just the sine curve where the amplitude is multiplied by 5, so it goes up to 5 and down to -5. And then we've translated left by 53.1 degrees. So I can just start with the sine curve and move it. And that is massively important. Now, the process is always the same, okay? We're going to have a look at this question B now. I'll work through it a little bit more quickly, but we're being asked to write this in the form 3 sine x plus 4 cos x. This time we're being asked to write it as r cos x minus an angle, which we call beta. Now that's important. Again, the understanding of the graphs is key here. You know that the cosine graph is just the sine graph shifted to the left by 90 degrees. All right, so there is that link there. So it stands to reason that we can write this 3 sine x plus 4 cos x as either sine or cosine. They're the same graph, just in a different place. So let's have a look and see what comes out when we apply the method. So r, same as before. We square both coefficients, we add them, and we square root the answer. Then we write out our identity. And I'm going to skip one line of working from before, nothing too serious. So I'm going to this time expand cos x minus beta. So I've got r cos x cos beta plus r sine x sine beta. And that's the expansion of cosine a minus b. Okay, if there's a minus in the bracket, then there's a plus because it's cosine, and I've multiplied by r already, so I've missed out this line and gone straight to this line. So again, here we compare our coefficients. We've got 3 lots of sine x, and on the right-hand side, we've got r sine beta lots of sine x. So we can say that r sine beta is equal to 3. And so for our second coefficient, we've got 4 lots of cos x. How many cos x's do we have? We've got r cos beta over on the right. So we've got the r cos beta equals 4. So therefore, tan beta is r sine beta divided by r cos beta, which is 3 over 4. So therefore, beta is arc tan 3 over 4, same working, and we'll go back and do that. So we'll do arc tan this time 3 over 4. We get 36.9 to 1 decimal place. You might be looking at this and thinking, oh, look at that. 53.1 and 36.9, add them together, you get 90, and you're absolutely right. And that's because the sine curve and the cosine curve differ by 90 degrees in the x direction. So let's finish off, and we'll put our little statement of fact. So 3 sine x plus 4 cos x is the same as 5 cos brackets x minus 36.9. And that makes perfect sense, I think. Both of these equal different things here, right? We've got 5 cos x minus 36.9, or we had 5 sine x plus 53.1. The 5s are multiplying the amplitude, which is fine. This is transforming the sine curve to the left by 53.1, whereas this is transforming the cosine curve to the right by 36.9. And that places them both in the same place. They are the same graph, and that's why these two are the same. So that's the method. That's how you work with this. Why do we use it? Well, we can use it to solve equations. So let's have a look at this question here. Sorry for the pause, just had to take a swig of coffee. It's very early. Okay, so we're going to express 2 cos theta plus 5 sine theta, and we're given the form r cos theta minus alpha. We're working in degrees, that's important to know. So we're going to go ahead and work out what our r is. We've got 2 squared plus 5 squared, which is going to be root 29, and we'll leave it as root 29. We're not going to evaluate that in any way as a decimal, I should say. We'll leave it as an exact value. And then we're going to go ahead and do our expansion. So we've got 2 cos theta plus 5 sine theta, which is r cos theta cos alpha plus r sine theta sine alpha, as before with the cosine expansion. We're going to compare our coefficients. 2 cos theta is the same as the r cos alpha cos theta. So r cos alpha is equal to 2. We've got our 5, which is equal to our r sine alpha. So r sine alpha is equal to the 5. So we can say that tan alpha is sine divided by cosine, 5 over 2. And therefore we can do arc tan of that and get our angle. So we'll do arc tan 5 over 2. And we get 68.2 degrees. So to finish the question off, we state what we found. 2 sine theta plus 5 sine theta is the same as root 29 cos theta minus 68.2 degrees. Okay? So we've now written this as a transformation of the cosine graph. We've multiplied the amplitude by root 29, and we've shifted the whole thing to the right by 68.2. So now we're being asked to solve, okay? So hence solve. Now we can solve this equation previously. We could divide by cosine and we could get tan. So we did have a method of working with this, but now we've got a different method. Now we can say this equation is the same as 29 cos theta minus 68.2 degrees equals 3. Okay, rewrite the equation using what you've just done. That's what this hence is telling you to do. So we make that equal to 3, and we go ahead and solve it. So we've got cos theta minus 68.2 is equal to 3 over root 29. Our limits I should have written down 0 to 360. So because we're working with an equation that's a linear function of theta, we're actually using the limits minus 68.2, theta minus 68.2, and 291.8. I believe. Yes, I can do arithmetic this early in the morning. Okay, so we'll do arc cos then. Theta minus 68.2 is arc cos of 3 over root 29. Do that. 56.1 as our initial value, and we'll do 360 minus this. So we get 303.9 degrees. Excuse me. And we've got our limits as well that we've got to be incredibly mindful of. This 56.1, if we think about our cosine graph behaves like this. So here's my 56.1. There will be another solution here at minus 56.1 that I've got to be mindful of. So minus 56.1, because it falls into these new limits, minus 68.2 that I've applied due to our transformation. So we've actually got these 3 solutions here, and over here is our 303.9. So therefore theta, we're just going to add our 68.2 to each of these. 6.1 plus 68.2, and we'll find that one of them is outside the limits, but we've got 124.3 degrees. We'll do minus 56.1 plus the 68.2, which is 12.1 degrees. And if we do the 303.9 plus the 68.2, we're going to find a value that is outside of our limits, as the 303.9 was. I should have paid attention to that. So we have our 2 solutions for theta. Okay, so that's one way that we use the R transformation to solve a nice equation. The second way is to answer one of these huge exam style questions. So you don't have to read all of it just now. You can pause the video and read it if you choose to. I'm going to break it down and work through it piece by piece. So the first part of this question says express this in this form. So we're getting used to this now, 2 sine theta minus 1.5 cos theta, which is r sine theta minus alpha. We're working in radians this time, so we need to be mindful of that. R is just the square root of 2 squared plus 1.5 squared. Don't worry about the minus. It all comes out in the wash because we're doing this. So we've got r is equal to, let's just work this out properly. We've got 2 squared plus 1.5 squared. So we've got 5 over 2. We'll write it as 2.5. So then we'll do our expansion. 2 sine theta minus 1.5 cos theta is the same as r sine theta cos alpha minus r cos theta sine alpha. And that's why the minus doesn't matter over here, because we've got a minus in our expansion. And then we just compare our coefficients. So 2 sine theta, so 2 is equal to r cos alpha. And then we've got 1.5 cos theta, which is our r sine alpha. So therefore, tan alpha is going to be 1.5 over 2. And we can work out alpha, again, remembering that we're working in radians. So we'll do arc tan of 5. We get 0.6435 to 4 decimal places. So then, So now we've got all of our information, and we can say that 2 sine theta minus 1.5 cos theta is the same as 2.5 sine theta minus 0.6435 radians. So that should be pretty standard by now. Hopefully we're getting to this point where this method is just ingrained. Part B, find the maximum value. So to find the maximum value, this is what I was talking about for the transformation of the graph. We've got 2.5 sine theta minus 0.6435. Now, the maximum value of this, you're thinking about the graph. How has this transformed the sine graph? Well, it's magnified its amplitude. Okay, it no longer goes up as high as 1 and as low as -1. It goes up as high as 2.5 and as low as minus 2.5. So the maximum value that this graph reaches is just 2.5. And that is always going to be the case. That's what this 2.5 does, multiplies the y values. So then we have find the value of theta at which this maximum occurs. Now, if you think about the sine curve, which is what we're working with after all, where does the maximum generally occur? It occurs at pi over 2 radians. So this is where our 2.5, if you like, would occur. Where does it now occur? Well, we've moved this graph to the right by 0.6435 radians. So instead of the maximum being pi over 2, it's pi over 2 plus 0.6435 because it's moved to the right. So we'll just say pi over 2 plus this 0.6435, and we'll just very quickly work that out on the calculator. Pi over 2 plus 0.6435, which is 2.21. It doesn't ask for an accuracy, so we'll say that that's correct to 3 significant figures. So this is where your understanding of the graph is massively important. If you know that graph, then this question is not going to cause you any problem whatsoever. So now we get into the hardest part of the question, I would say. Tom has modeled the height of seawater in H meters by this equation. Now, don't look at this equation and think, what on earth is going on? Look at this equation and think, how does it compare to my equation? Because that's what they're asking you to do. So we've got 6 plus 2 sine 4 pi t over 25 minus 1.5 cos 4 pi t over 25. Now, how does this compare? Well, 2 sine theta minus 1.5 cos theta. It's just theta's different. And then we've got this 6. So actually, this equation we can write using our transformation. We've got 2.5 sine theta, which is 4 pi t over 25, minus 0.6435. All right? And I've forgotten there, but we mustn't forget, is at the beginning, we've got 6 plus. Okay? That's the bit we're adding in. So this should be pretty straightforward now that we've made that connection. Calculate the maximum value of h predicted by this model and the value of t to 2 decimal places when this maximum occurs. So from the previous question, we knew that the maximum would be 2.5. And that's still the case here. For this part of this equation, 2.5 is the maximum, like before. Then what's happened? Well, we've added 6. So the maximum is as simple as saying 6 plus 2.5, which is 8.5 meters. Now we need the units because we're now working in a real world problem. So we have h meters, so 8.5 meters is our maximum. What time does this occur? So the value of t to 2 decimal places when this maximum occurs. Well, where does it occur? It occurred, if you remember, we took our pi over 2 and we added 0.6435. Okay? So that's kind of basically saying the same thing as this 4 pi t over 25 minus 0.6435 is equal to, oh, forgive me. Okay, right. So this equals this pi over 2. Okay, that's where the maximum on the sine curve occurs at pi over 2. So this part in the brackets for sine has to be pi over 2. And now what we're doing is we're just solving t. So t is going to be equal to pi over 2 plus 0.6435. So we've added the 0.6435. We're multiplying that by 25. And then we're dividing it by 4 pi, which seems a bit complicated, but we can certainly manage. So we use the fraction button on the calculator and just plow into that. So we've got 25 multiplied by pi by 2 plus 0.6435 divided by 4 pi. And so t is 4.2 decimal places, 4.41 hours. Okay. So just to kind of recap that, the maximum happens at 2.5, but then add 6. When does it happen? Well, this thing in the bracket has to be equal to pi over 2 because pi over 2 creates the first maximum on the sine curve. And so we just make that equation and solve it for t. All right, so now we're into what is basically solving an equation. Calculate to the nearest minute the times when this is equal to 7 meters. So that means we're looking at 7 equals 6 plus 2.5 sine 4 pi t over 25 minus 0.6435. And we're just going to go ahead and solve this equation. So 1, take away 6 from both sides, is 2.5 sine 4 pi t over 25 minus the 0.6435. Divide both sides by 2.5, so we get 2/5 is sine 4 pi t over 25 minus 0.6435. So we'll do arc sine of both sides. We get arc sine of 2/5, which is 0.4115. And that equals my 4 pi t over 25 minus 0.645. Now we also have to remember that's not our only solution. We're going to have to, using the sine curve, the sine transformation, we're going to have to say that we use pi minus this answer as well. So we'll do pi minus the answer. And we get 2.73 is our other answer, 2.73. And then it's about solving t for both of these. So therefore, t is going to be our 0.4115 plus 0.6435 multiplied by 25 and then divided by 4 pi, just like we did before. So if we do that, we'll do our 0.4115 plus 0.6435 multiplied by 25 divided by 4 pi, and we get 2.09 hours. Now 2.09 hours after midday, well, we need to find 0.09. So 0.09 hours is how many minutes? We just multiply that by 60. Now we get 5.4 minutes. So 2 hours, 5.4 minutes after midday. The time is 14:05 to the nearest minute. We'll do the same thing now for our other value of t. And we'll say t is equal to our 2.73 plus the 0.6435 multiplied by the 25 divided by the 4 pi. We're nearly there. Work that out. So 2.73 plus 0.6435 multiplied by 25, just doing it on the calculator as we speak, divided by 4 pi, which is 6.71 hours. And again, 0.71 hours is how many minutes? We'll take that and multiply by 60. It's 42.6 hours minutes, so 43 minutes to the nearest minute. So we have 6 hours, 43 minutes. So we have 6:43 p.m. or 18:43. And that is the R method. That's how you do it. That's how you solve an equation with it. And that's how you attack a complicated real-world problem. I hope this video was of some use. You can go back and pause, obviously, if you need help with it. Apologies that it is 30 minutes long. Happy with